Welcome back to our Introduction to Control Theory series. In this episode, we'll delve into the fundamental components of control systems, the plant, the controller, and the feedback loop. Over the next hour or so, we'll explore their vital roles and how they collaborate to shape the behavior of control systems. This is the second part, where we'll discuss the controller and the feedback loop. In part 1 of this video, we address the plant. Click the card at the top if you haven't watched the first part yet. As we venture further into the intricate world of control systems, our attention turns to the controller, the central brain behind the system's operation. The controller is responsible for processing information, analyzing feedback, and making control decisions with the precision of a skilled conductor leading an orchestra. In this section, we'll dive deep into the multifaceted functions of the controller, exploring various types, including the widely used PID controller and their digital counterparts. To bring this abstract concept closer to reality, we'll dissect a practical example, a temperature control system. Through this lens, we'll illuminate how a PID controller orchestrates the maintenance of a desired temperature, showcasing the elegance and efficiency of control strategies in action. At its core, the controller serves as the nerve center of a control system. These are its primary functions. In the intricate dance of control systems, feedback processing emerges as a critical and ceaseless task undertaken by the controller. It serves as the control system's watchful eye, continuously gathering data about the system's performance and dynamics. Imagine it as the vigilant conductor who listens attentively to the orchestra's performance, ensuring that every note aligns with the intended masterpiece. Feedback processing entails the constant acquisition of data from sensors strategically placed within the system. These sensors serve as the sensory organs, providing the controller with a real-time stream of information about the system's state. They measure parameters such as temperature, pressure, position, velocity, and any other relevant variables, depending on the application. This data stream forms the foundation of the controller's understanding, much like an artist observing every detail of their subject before creating a masterpiece. The feedback loop is a dynamic conversation between the system and the controller. As the system operates, sensors continuously transmit measurements to the controller. These measurements reflect the system's actual state and performance. The controller, in turn, interprets this data, scrutinizing it for any deviations from the desired or set point values. It's a bit like a pilot relying on an instrument panel to monitor the aircraft's altitude, speed, and heading during flight. The pivotal role of feedback processing becomes evident when the controller identifies an error. The error represents the numerical difference between the desired set point and the actual measured value of a system's output. This error quantifies the deviation from the intended target. The controller's ability to recognize and interpret this error is akin to a conductor detecting a note out of tune amidst the symphony, ready to take corrective action. The real-time nature of feedback processing ensures that the controller is in constant dialogue with the system it governs. As the system operates, the controller dynamically adjusts its responses based on the incoming feedback data. It's like a conductor who alters their gestures and cues to guide the orchestra through tempo changes, ensuring that the music flows seamlessly. Feedback processing is the heartbeat of a control system, supplying it with the vital signs needed for precise and dynamic control. Through this ongoing exchange of information, the controller gains an intimate understanding of the system's behavior, allowing it to make informed control decisions. As we continue our exploration of control theory, remember that feedback processing is the sensory perception that enables the control system to respond with finesse and accuracy to achieve our desired objectives. In the intricate realm of control systems, error calculation emerges as a pivotal step in the controller's decision-making process. It's akin to a skilled navigator meticulously measuring the distance between their current position and their desired destination. This calculation quantifies the deviation between the intended set point and the actual measured value of the system's output, serving as the basis for informed control decisions. At the heart of error calculation lies a fundamental question: how far are we from the desired destination? In the context of control systems, this question translates to: how different is the actual system's output from the desired set point? The error is the numerical representation of this difference. It's a value that signifies the system's current state of alignment with the intended target. This quantification of the deviation provides the controller with a precise and tangible metric to work with. Control engineers often employ proportional control, one of the components in PID, or proportional integral derivative controllers, to determine the control action based on the error. In proportional control, the control action is directly proportional to the error magnitude. This means that the larger the error, the greater the corrective action applied by the controller. It's akin to a navigator adjusting their course more aggressively when they realize they are further from their desired path. The beauty of error calculation lies in its immediacy. As soon as the error is determined, the controller can initiate a corrective response. There's no delay in recognizing or responding to deviations from the desired set point. This immediacy ensures that control systems can maintain precise and dynamic control, adapting rapidly to changing conditions. Error calculation is not a static process. It's a dynamic one. As the system operates and feedback data continuously updates, the error is recalculated in real time. This dynamic nature allows the controller to respond to evolving conditions and maintain the system's alignment with the desired set point. It's akin to a skilled athlete adjusting their movements on the fly to maintain peak performance. Error calculation is the compass that guides the controller on its journey to precise control. It quantifies the discrepancy between where the system currently stands and where it should be, providing the controller with the information needed to make timely and informed control decisions. As we continue our exploration of control theory, remember that error calculation is the cornerstone of control systems' ability to achieve desired outcomes with accuracy and efficiency. In the intricate tapestry of control systems, control decision-making emerges as a cerebral center where the controller processes feedback, interprets the error, and orchestrates control actions with the precision of a seasoned conductor leading an orchestra. This multifaceted task is the essence of control, where every decision is a note in the symphony of system operation. At the core of control decision-making lies the interpretation of error. The error is the controller's guidepost, telling it how far the system is from the desired set point. But it's not just a numerical value. It's a message that communicates the system's state of alignment with the intended target. The controller scrutinizes the error, discerning whether it's a minor deviation that requires gentle adjustment or a significant divergence demanding a more robust corrective action. Armed with the understanding of this error, the controller faces the critical task of selecting the appropriate control action. This decision-making is guided by control algorithms tailored to the specific system and application. In the case of a proportional controller, the control action is directly proportional to the error magnitude. For more complex systems, such as those utilizing PID controllers, the decision-making process involves considering proportional, integral, and derivative components to achieve precise and adaptive control. Control decision-making is not a one-time event, but a continuous process. As the system operates, feedback data keeps streaming in, and the error is continuously recalculated. The controller must adapt its control actions in real time to ensure the system maintains alignment with the desired set point. It's akin to a conductor leading an orchestra through a dynamic musical piece, adjusting tempo and intensity to maintain harmony. The art of control decision-making is about achieving precision and stability. Control actions must be calculated with finesse, ensuring that they neither overshoot the mark nor lag behind. The controller strives to bring the system's response as close as possible to the desired set point while maintaining stability. It's a delicate balance, much like a tightrope walker navigating a narrow path. Control decision-making is the soul of a control system, where the abstract concept of error transforms into concrete actions that guide a system towards the desired outcomes. It's a constant interplay of interpretation, calculation, and adaptation that ensures systems operate with the utmost precision and efficiency. As we continue our journey through control theory, remember that control decision-making is the conductor's baton that leads the symphony of control with grace and mastery. In the intricate world of control systems, output generation stands as the culmination of meticulous analysis, error calculation, and control decision-making. It's the moment when the controller's wisdom and precision manifest as concrete commands that actuate the system, much like a conductor's final flourish that brings the orchestra to life. In this section, we'll explore how control systems generate and apply output signals with the aim of achieving precise and dynamic control. The essence of output generation lies in translating the control decisions made by the controller into tangible actions. These actions take the form of output signals, which control the system's actuators, motors, and other devices to implement the control strategy. It's akin to the conductor's gestures that instruct the orchestra to play louder, softer, faster, or slower, translating their musical interpretation into real-time performance. Control systems strive for precision in output generation. The control action, quantified based on error and control algorithm, is carefully calculated to bring the system's response in alignment with the desired set point. This precision ensures that the system operates with accuracy, minimizing deviations and errors. It's like a master craftsman who chisels away imperfections to reveal the perfect form beneath. Just as control decision-making is a dynamic process, output generation is also dynamic. As feedback data continuously updates and the error is recalculated, the controller adapts its control action in real time. This means that the output signal is not a static command, but an evolving one, allowing the control system to respond promptly to changing conditions. It's akin to a seasoned driver who makes constant adjustments to the steering wheel to maintain a steady course on a winding road. The output signal not only commands the system, but also completes the feedback loop. When the system responds to the output signal, it generates a new measurement that are fed to the controller. This closure of the feedback loop initiates a continuous cycle of monitoring, calculation, and adjustment. It's akin to the musician who listens to the orchestra's performance and adapts their conducting to ensure the music remains in harmony. Output generation is the moment of truth in control systems, where decisions become actions and theory transforms into practice. It's the culmination of a complex process that ensures the system operates with precision, accuracy, and responsiveness. As we continue our exploration of control theory, remember that output generation is the conductor's baton that transforms the cacophony of data and calculations into a symphony of control, achieving our desired outcomes with artistry and grace. Among the arsenal of controllers, the PID, Proportional Integral Derivative Controller, is the stalwart. It employs a combination of proportional, integral, and derivative actions to achieve precise control. The proportional component responds to the current error. The integral component corrects for accumulated past errors. And the derivative component anticipates future errors based on the rate of change. PID controllers are workhorses in control systems, excelling in applications ranging from industrial processes to robotics and beyond. PID controllers are renowned for their ability to achieve precise and dynamic control in various industrial and technological applications. The name PID stands for the three primary control actions they employ: proportional, integral, and derivative. The proportional component responds to the current error, which is the difference between the desired set point and the actual measured value of the system's output. It calculates a control action that is directly proportional to the magnitude of the error. In simple terms, when the error is large, the proportional action commands a more significant correction, and when the error is small, it prescribes a more subtle adjustment. This component provides immediate and responsive control. The integral component addresses accumulated past errors. It calculates an action based on the integral or sum of the error over time. This is particularly valuable when there are persistent errors that the proportional action alone cannot eliminate. The integral action gradually reduces long-term deviations from the set point, ensuring that the system reaches and maintains the desired value. The derivative component anticipates future errors based on the rate of change of the error. It calculates an action that opposes rapid changes in error. This is especially useful in preventing overshooting or oscillations around the set point. The derivative action adds a layer of stability to the control system, ensuring a smooth and controlled response. PID controllers are celebrated for their adaptability. They can be fine-tuned to match the specific characteristics and requirements of a system. Control engineers can adjust the proportional, integral, and derivative gains to optimize the controller's performance. This adaptability makes PID controllers highly versatile and suitable for a broad spectrum of applications. PID controllers find applications in diverse fields, including temperature regulation in industrial processes, position control in robotics, speed control in motor drives, and many more. They excel in scenarios where precise and rapid control is essential. While PID controllers are powerful, they are not without challenges. Tuning PID controllers to a specific system can be a complex task, requiring an understanding of the system's dynamics and control objectives. Additionally, PID controllers may struggle with nonlinear or highly variable systems, which may necessitate more advanced control techniques. PID controllers are the cornerstone of precise control in countless industries. Their ability to adapt, respond in real time, and achieve dynamic control makes them indispensable tools for control engineers. As we continue our exploration of control theory, remember that PID controllers are the maestros of control, orchestrating systems with finesse and accuracy to meet our desired objectives. In the digital age, controllers have evolved to embrace digital technology. Digital controllers, equipped with advanced algorithms and computing power, offer enhanced control capabilities and flexibility. They can handle complex tasks, implement sophisticated control strategies, and adapt to changing conditions with agility. Digital controllers represent a significant evolution in control technology, harnessing the power of digital computing to achieve precise, adaptable, and robust control in a wide range of applications. Here's a more comprehensive look at digital controllers. The defining feature of digital controllers is their utilization of digital computation for control tasks. Unlike their analog counterparts, which operate using continuous signals, digital controllers work with discrete data, processing information in a step-by-step fashion. This transformation from analog to digital enables more advanced control algorithms and greater flexibility in handling complex systems. Digital controllers are equipped with advanced control algorithms that can adapt to changing conditions and optimize system performance. They are capable of implementing complex control strategies, such as modeled predictive control or adaptive control, which can be challenging to achieve with analog controllers. This advanced capability is invaluable in applications where precision and adaptability are paramount. Digital controllers rely on a sampling process to convert continuous signals from sensors into discrete data points. This process, known as discretization, introduces considerations such as sampling frequency and signal quantization. Control engineers must carefully select appropriate sampling rates to capture the dynamics of the system effectively. Digital controllers are inherently robust in noisy environments. The discrete nature of digital signals helps filter out noise, ensuring the controllers make decisions based on clean data. This noise resistance is particularly advantageous in industrial settings, where sensors may be exposed to electrical interference and environmental disturbances. In the era of Industry 4.0, digital controllers often integrate with digital twin technology. A digital twin is a virtual replica of a physical system, and it allows for real-time monitoring, simulation, and optimization. Digital controllers can leverage digital twins to enhance their decision-making processes, predicting system behavior and optimizing control strategies. Digital controllers find applications in diverse industries, including manufacturing, aerospace, automotive, and process control. They are especially prevalent in applications where precise control, adaptability to varying conditions, and data-driven decision-making are essential. While digital controllers offer numerous advantages, they are not immune to challenges. Implementing digital controllers requires expertise in digital signal processing, control theory, and programming. Additionally, concerns related to cybersecurity and data integrity must be addressed, especially in critical infrastructure applications. Digital controllers represent the cutting edge of control technology in the digital age. Their ability to process discrete data, implement advanced control strategies, and adapt to dynamic environments makes them indispensable in modern control systems. As we continue our exploration of control theory, remember that digital controllers are the digital maestros orchestrating precise and adaptive control in an increasingly interconnected and data-driven world. Imagine a scenario in a manufacturing facility where precise temperature control is critical for the quality and safety of a chemical process. In this controlled environment, a temperature control system takes center stage, ensuring that a specific temperature set point is maintained with a high degree of accuracy. Let's delve deeper into how a PID controller orchestrates this process. The journey begins with the definition of a set point. Control engineers specified the desired temperature that a system must achieve and maintain. This set point serves as the target, much like a destination on a map. Sensors strategically placed within the system continuously monitor the temperature. These sensors act as the system's sensory organs, sending real-time temperature data to the PID controller. This feedback allows the controller to know the system's current state, much like a pilot relying on instruments to navigate an aircraft. As the temperature sensors transmit data, the PID controller calculates the error. This error represents the difference between the desired set point and the actual measured temperature. If, for instance, the set point is 100 degrees Celsius and the measured temperature is 98 degrees Celsius, the error is -2 degrees Celsius, indicating that the system is cooler than desired. The proportional component of a PID controller responds to the error. In our example, the proportional action would calculate a control output proportional to the -2 degrees Celsius error. This calculated output might involve increasing the heating element's power to raise the temperature. Over time, if the system consistently deviates from the set point, the integral component of the PID controller comes into play. It accumulates the past errors and applies corrective action. For instance, if the system has been consistently below the set point, the integral action would gradually increase power to the heating element to compensate for this prolonged deviation. The derivative component of the PID controller anticipates future errors by assessing the rate of temperature change. If the temperature is rapidly approaching the set point, the derivative action may reduce the power to the heating element to prevent overshooting the target. The PID controller continuously recalculates the control output based on the error in the three control actions, P, I, and D. It adapts its decisions in real time as feedback data updates. This dynamic process ensures that the temperature remains as close as possible to the desired set point with minimal fluctuations. Through this intricate dance of feedback, error calculation, and control actions, the PID controller achieves precision and stability in maintaining the desired temperature. It ensures that the chemical process proceeds with accuracy, maximizing product quality and safety. The beauty of PID controllers lies in their versatility. They can be tuned to suit various systems and applications. Control engineers can adjust the PID gains to optimize performance for specific temperature control requirements. This practical example illustrates how a PID controller orchestrates the symphony of temperature control in a manufacturing process. It showcases the power and adaptability of control strategies in ensuring that critical processes run with the utmost precision and efficiency. Now, let's talk about the feedback loop, an often underestimated component. Feedback provides crucial information about the system's performance. We'll discuss its significance and explore the differences between open-loop and closed-loop systems. To drive the point home, we'll look at how feedback plays a pivotal role in maintaining the stability of aircraft during flight. The feedback loop, often overlooked but fundamentally essential, serves as the heartbeat of control systems. It's the dynamic conduit through which control systems continuously gather information about its own performance, interprets the data, and adapts its actions to achieve precise control. Let's delve deeper into why feedback is crucial and explore the differences between open-loop and closed-loop systems. To bring this component to life, we'll examine how feedback plays an indispensable role in ensuring the stability of aircraft during flight. Imagine a control system as an explorer navigating through uncharted territory. Without feedback, it would be akin to setting sail without a compass or map. Feedback provides this essential guidance, offering a constant stream of information about the system's current state. This data encompasses variables such as temperature, pressure, position, speed, and any other relevant parameters, depending on the system's purpose. In open-loop systems, feedback is absent or not utilized in the control process. It's like giving an explorer no means to determine their current location or adjust their course based on changing conditions. Open-loop systems are often simple and suitable for processes where precision and adaptation aren't critical. However, they are susceptible to disturbances and inaccuracies. Closed-loop systems, on the other hand, embrace feedback wholeheartedly. They continuously monitor the system's performance, comparing it to the desired set point. This comparison generates an error that signifies the deviation from the target. Closed-loop systems then use this error to make real-time adjustments to control actions, much like an experienced navigator adjusting their course to stay on track. This inherent adaptability and precision make closed-loop systems the preferred choice for applications demanding accuracy and stability. Aircraft provide a compelling example of how feedback ensures stability and safety. During flight, numerous sensors throughout the aircraft measure critical parameters like altitude, airspeed, and attitude. This wealth of data feeds into a closed-loop control system, often known as a flight control system. When the pilot sets a desired altitude, for instance, the feedback loop constantly evaluates the actual altitude. If the aircraft deviates from the desired level, the feedback system takes corrective action, adjusting control surfaces like ailerons, elevators, and rudders to bring the aircraft back on course. This continuous monitoring and adaptation maintain the aircraft's stability, ensuring that it responds to turbulence, wind, and other dynamic factors with grace and precision. In the broader landscape of control systems, feedback is not a mere component. It's the linchpin that ensures precision, stability, and adaptability. It's the guardian that watches over the system's performance, ensuring it stays on course and aligns with our objectives. As we continue our journey through control theory, remember that feedback is the guiding star that allows control systems to navigate complex and dynamic terrains, achieving our desired outcomes with unwavering accuracy and poise. But what makes control systems truly intriguing is how the components interact. Changes in one component can have a ripple effect across the entire system. To grasp this, we'll analyze real-world case studies. These examples span various industries, from industrial automation to automotive control, illustrating how these components come together to achieve precise control. Control systems are akin to orchestras, where various instruments, each representing a control system component, harmonize to produce a beautiful symphony of control. What truly makes control systems intriguing is the intricate dance of interactions between these components. Changes in one element can set off a cascade of effects throughout the system, and understanding these interactions is key to mastering control theory. Imagine a conductor leading an orchestra. When the conductor raises his baton, it signals the musicians to start playing. As they play their instruments, each musician listens to the music around them and adapts their performance accordingly. If one musician speeds up or slows down, it can influence others, necessitating adjustments to maintain harmony. In control systems, this dynamic interplay is analogous to the interactions between components. Changes in one control component can create ripple effects that propagate throughout the system. For instance, adjusting the gain in a controller, like a PID controller, impacts how it responds to errors. This, in turn, affects the control action it sends to the actuator. The actuator's response alters the system's output, which is then measured by sensors and fed back to the controller. This continuous loop of interactions can lead to subtle adjustments or dramatic changes in system behavior. To truly grasp these interactions, we'll delve into real-world case studies from diverse industries. These examples showcase how control system components work in concert to achieve precise control. Industrial automation represents the pinnacle of control system application, revolutionizing the way we manufacture goods. It's the art and science of using control systems to oversee and optimize industrial processes, ensuring efficiency, quality, and safety. Here's a comprehensive look of how control systems make industrial automation possible. In industrial settings, numerous processes need to be executed with precision and consistency. This process can range from chemical reactions in the pharmaceutical plant to assembly lines in automotive manufacturing. Control systems play a pivotal role in optimizing these processes. They monitor critical parameters such as temperature, pressure, flow rates, and quality metrics to make real-time adjustments and ensure that the process operates within desired specifications. Industrial automation relies on a network of sensors strategically placed throughout the production environment. These sensors act as the eyes and ears of the control system, constantly feeding data back to the central controller. For instance, in a chemical plant, sensors monitor factors like temperature, pressure, and chemical concentrations. This continuous stream of data allows the control system to make informed decisions in real time. The heart of industrial automation lies in sophisticated control algorithms. These algorithms encompass various control strategies, from basic proportional control to more advanced techniques like model predictive control. The choice of control algorithm depends on the nature of the process and the desired control objectives. For instance, in a chemical reactor, the control system may use a combination of proportional, integral, and derivative control to maintain a desired temperature and pressure. Control systems in industrial automation interface with actuators and devices that execute control actions. These can include motors, valves, pumps, and heating elements, among others. For instance, in a manufacturing plant, motors drive conveyor belts, Valves control the flow of liquids, and heating elements regulate temperature. The control system sends signals to these actuators, dictating their actions based on the feedback received from sensors. Safety is paramount in industrial automation. Control systems incorporate redundant systems and fail-safes to ensure that critical processes can be shut down or switched to safe mode in case of emergencies. This redundancy provides an added layer of protection, safeguarding both personnel and equipment. Precision control in industrial automation directly translates to product quality. Control systems meticulously regulate parameters to meet quality standards. For instance, in a food processing plant, control systems ensure that temperature, cooking times, and ingredient proportions are precisely controlled to produce consistent, high-quality products. Industrial automation not only ensures precision, but also enhances efficiency and productivity. By automating routine tasks and optimizing processes, control systems reduce human error, minimize downtime, and increase throughput. This leads to higher production yields and cost savings for industries. Control systems in industrial automation are designed to adapt to changing conditions. They can adjust control parameters based on factors like raw material variations, environmental conditions, and equipment wear and tear. This adaptability ensures that processes remain on target even in dynamic operating environments. Industrial automation exemplifies how control systems revolutionize production processes. By combining continuous monitoring, sophisticated control algorithms, and precise actuation, control systems in industrial automation drive efficiency, quality, and safety across a wide range of industries. As we explore this facet of control theory, remember that industrial automation represents the zenith of precision control, shaping the landscape of modern manufacturing. The automotive industry is a testament to the transformative power of control systems. Vehicles today are marvels of engineering, and at the heart of their performance and safety lies a web of sophisticated control systems. Here's a comprehensive look of how control systems make automotive control possible. The engine is the heart of any vehicle, and control systems govern its operation with precision. Engine control units continuously monitor various parameters, such as fuel mixture, ignition timing, and exhaust emissions. Control algorithms optimize combustion efficiency, resulting in improved fuel economy, reduced emissions, and enhanced performance. Additionally, electronic throttle control systems ensure smooth acceleration by regulating the throttle based on the driver's input and sensor data. Automatic and semi-automatic transmissions rely on control systems to manage gear selection and shifting. Transmission control modules analyze factors like vehicle speed, engine load, and driver behavior to determine the optimal gear ratio. This not only enhances drivability, but also contributes to fuel efficiency. Anti-lock braking systems is a safety-critical component that prevents wheels from locking up during hard braking, ensuring steering control and stability. ABS control systems monitor wheel speed using sensors and adjust brake pressure to each wheel independently to prevent skidding. This real-time adaptation is crucial in emergency braking situations. Electronic stability control systems continuously monitor vehicle dynamics, including yaw rate and wheel speed. If the vehicle's behavior indicates a potential loss of control, the ESC system intervenes by selectively applying brakes to individual wheels and adjusting engine power to stabilize the vehicle. This technology has significantly improved vehicle safety. Cruise control systems allow for maintaining a set speed without continuous driver input. They use control algorithms to regulate throttle and braking, ensuring that the vehicle remains at the desired speed. Modern adaptive cruise control systems also incorporate sensors to adjust speed based on traffic conditions. Power steering systems utilize control valves and sensors to assist with steering effort. These systems adapt the level of assistance based on the vehicle speed and driver input, providing ease of steering at low speeds and stability at high speeds. Control systems play a critical role in airbag deployment. Sensors throughout the vehicle monitor impact forces and deploy airbags within milliseconds of a collision. Precise timing and control are essential to ensure airbags inflate at the right moment to protect occupants. Modern vehicles feature advanced infotainment and navigation systems with touchscreen interfaces. These systems are controlled by software and user interfaces, enabling drivers to access information, entertainment, and navigation services. The future of automotive control lies in autonomous driving systems. These systems integrate sensors, cameras, LiDAR, radar, and control algorithms to enable vehicles to operate without human intervention. Autonomous driving vehicles is a complex field involving machine learning and artificial intelligence. Control systems regulate climate control in vehicles, ensuring cabin comfort. They adjust temperature, fan speed, and airflow based on driver preferences and external conditions. Advanced systems can even control seat heating and cooling. Automotive control systems are the driving force behind modern vehicles. They encompass engine management, safety features, drivetrain control, and infotainment. These systems enhance vehicle performance, safety, and comfort, while also contributing to fuel efficiency and reduced emissions. As we explore the realm of automotive control, remember that control systems are the invisible hand guiding your vehicle's every move, ensuring precision in motion. Aerospace control systems are the guardians of flight, ensuring that aircraft, spacecraft, and drones operate with precision, stability, and safety. These systems are characterized by their complexity and the unique challenges they face in harsh environments of the sky and space. Here's a comprehensive look of how control systems make aerospace control possible. The core of aerospace control lies in flight control systems. These systems manage the aircraft's orientation or attitude, altitude, heading, and speed. They consist of sensors, control algorithms, and actuators. Sensors, such as gyroscopes and accelerometers, continuously measure the aircraft's position and movement. Control algorithms interpret this data and send commands to actuators, like control surfaces and engines, to adjust the aircraft's flight parameters. This dynamic interplay keeps the aircraft stable and responsive to pilot input. Autopilot systems relieve pilots of the constant need for manual control during flight. They are intricate control systems that can maintain straight and level flight, execute precise turns, and even handle complex maneuvers. Autopilots integrate various sensors such as GPS, airspeed, and altitude sensors to make autonomous decisions and keep the aircraft on course. Many modern aircraft employ fly-by-wire systems, replacing traditional mechanical control linkages with electronic systems. FBW systems provide fine-grained control over aircraft behavior, allowing for envelope protection, enhanced maneuverability, and reduced weight. These systems continuously monitor pilot input and aircraft state to provide a smooth and precise flying experience. Aerospace control is heavily reliant on avionics systems. These systems encompass a wide range of electronics and software that support flight, navigation, communication, and mission-specific tasks. For example, the avionics suite of a commercial airliner includes flight management systems, radar systems, and communications equipment. Beyond Earth's atmosphere, control systems play a critical role in spacecraft. They manage attitude control to ensure spacecraft orientation, propulsion for trajectory adjustments, and communication with mission control on Earth. Spacecraft often operate in extreme conditions, making control and navigation systems particularly challenging. Drones and unmanned aerial vehicles are rapidly evolving aerospace platforms that rely on advanced control systems. These systems enable precise navigation, obstacle avoidance, and autonomous missions. UAV control also extends to military applications, surveillance, and even package delivery services. Supersonic and hypersonic aircraft push the boundaries of control theory due to their high speeds and unique aerodynamics. Control systems for these aircraft must manage shock waves, extreme temperatures, and rapid maneuvers. Aerospace control systems prioritize safety above all else. Redundant systems and fail-safes are built into aircraft and spacecraft to ensure they can handle emergencies. For example, automatic landing systems can guide aircraft safely to the ground in low visibility conditions. Aerospace control systems vary greatly depending on the mission. For instance, space probes may require autonomous navigation to distant planets, while military aircraft might employ stealth and electronic warfare capabilities. Aerospace control systems are the sentinels of the skies and beyond. They exemplify precision and reliability in environments where human lives and valuable cargo are at stake. These systems continuously adapt to dynamic conditions, ensuring that aircraft, spacecraft, and drones perform their missions with precision and safety. As we explore aerospace control, remember that control systems are the invisible hands that guide aircraft through the boundless skies and into the frontiers of space. Robotics represents the epitome of control system applications, blending mechanical, electrical, and software engineering to create machines that mimic or augment human capabilities. These intelligent machines, guided by sophisticated control systems, are revolutionizing industries ranging from manufacturing to healthcare. Here's a comprehensive look at how control systems make robotics possible. Robots rely on a diverse array of sensors to perceive their environment. These sensors can include cameras, LiDAR, ultrasonic sensors, touch sensors, and more. Control systems process the data from these sensors to create a digital representation of the robot's surroundings, enabling it to make informed decisions. Precise motion control is the hallmark of robotics. Control systems govern the movement of robotic arms, legs, wheels, and any other type of locomotion. Kinematics and dynamics algorithms are used to calculate and control joint angles, positions, velocities, and torques. This precision is crucial for tasks such as picking up and placing objects, assembly, and even surgical procedures. Path planning algorithms allow robots to autonomously navigate their environment while avoiding obstacles. Control systems take into account the robot's current state, the desired destination, and the obstacles detected by sensors to generate safe and efficient paths. For robotic arms and hands, control systems orchestrate complex movements for tasks like picking up objects, assembling components, or performing delicate surgeries. Advanced grasping algorithms determine how to grip objects securely. Mobile robots, such as autonomous vehicles and drones, rely on control systems to navigate and make real-time decisions about their paths. These systems integrate sensor data with algorithms from localization, mapping, and obstacle avoidance. Control systems enable robots to interact with humans in a safe and intuitive manner. Human-robot interaction technologies include speech recognition, gesture recognition, and facial recognition, allowing robots to understand and respond to human commands and emotions. In applications like warehouse automation or swarm robotics, multiple robots must work together efficiently. Control systems manage the coordination and communication between robots to achieve collaborative tasks. Robotics increasingly incorporates machine learning and artificial intelligence to enhance decision-making. Control systems can include neural networks and reinforcement learning algorithms for tasks like pattern recognition, object classification, and adaptive behavior. In healthcare, robotic control systems are used in surgery for tasks that require extreme precision. Surgical robots assist surgeons in performing minimally invasive procedures with enhanced dexterity and accuracy. In the context of Industry 4.0, robots are central to smart manufacturing. Control systems enable robots to work collaboratively with humans, adapt to changing production demands, and perform tasks like quality inspection and material handling. Robotic exoskeletons are wearable devices that assist individuals with mobility impairments or augment physical abilities of workers. Control systems monitor user movements and apply forces as needed to support or enhance human capabilities. Robotics is the convergence of mechanics, electronics, and software, with control systems as the orchestrators of these elements. These systems enable robots to perceive their surroundings, make informed decisions, and execute precise actions. From manufacturing and healthcare to exploration and entertainment, robotics is shaping the future where intelligent machines collaborate seamlessly with humans to achieve a wide range of tasks with precision and efficiency. Environmental control systems are the unsung heroes of our built environments, ensuring that spaces are comfortable, safe, and energy efficient. These systems regulate temperature, humidity, air quality, and lighting to create optimal conditions for occupants. Here's a comprehensive look of how control systems make environmental control possible. Heating, ventilation, and air conditioning systems are the backbone of environmental control in buildings. Control systems manage the operation of HVAC components, such as furnaces, air conditioners, ventilation fans, and ductwork. They monitor indoor and outdoor conditions and adjust parameters like temperature and airflow to maintain a comfortable and healthy indoor environment. Precise temperature control is essential for occupant comfort and energy efficiency. Control systems use feedback from temperature sensors to adjust heating and cooling systems, ensuring that their indoor temperatures remain within desired set points. Controlling humidity levels is crucial for preventing mold growth, preserving building materials, and maintaining occupant comfort. Control systems integrate humidifiers, dehumidifiers, and ventilation systems to regulate humidity levels in indoor spaces. Indoor air quality control systems monitor and manage the quality of the air we breathe. They incorporate sensors for pollutants like carbon dioxide, volatile organic compounds, and particulate matter. Based on sensor readings, control systems adjust ventilation rates and filtration systems to ensure fresh and clean indoor air. Lighting systems play a dual role in environmental control by enhancing visibility and influencing occupant well-being. Control systems for lighting include sensors that detect natural light levels and occupancy. These sensors adjust artificial light levels accordingly to maximize energy savings while maintaining adequate illumination. Building automation systems serve as the central nervous system of environmental control in modern buildings. These systems integrate various control components, including HVAC, lighting, security, and fire safety. They provide a united interface for monitoring and controlling building systems, optimizing energy usage, and ensuring occupant comfort. Environmental control systems are at the forefront of efforts to improve building energy efficiency. Control systems implement strategies like demand-controlled ventilation, setback temperatures during unoccupied hours, and predictive HVAC control algorithms to reduce energy consumption while maintaining comfort levels. Smart thermostats and building control platforms leverage advanced algorithms and data analytics to optimize HVAC operation based on factors like weather forecasts, occupancy patterns, and user preferences. These systems learn from user behavior and adjust settings to achieve energy savings without sacrificing comforts. Environmental control systems are integral to sustainable building designs. They incorporate renewable energy sources, such as solar panels and geothermal systems, and integrate with building materials that enhance thermal insulation and passive cooling. Environmental control systems often collaborate with safety and security systems to ensure occupant well-being. For example, they can activate ventilation systems in response to fire alarms to prevent smoke buildup. Environmental control systems are the linchpin of modern building design. They create environments that foster productivity, health, and well-being while minimizing energy consumption and environmental impact. From smart thermostats in homes to sophisticated building automation systems in commercial buildings, control systems are the invisible hand that balances comfort and efficiency in our indoor spaces. Understanding these interactions between components is the key to mastering control theory. Control engineers must be adept conductors, orchestrating these components to achieve desired outcomes with precision and efficiency. Just as the conductor ensures each musician plays in harmony, control engineers ensure that sensors, controllers, actuators, and feedback mechanisms collaborate seamlessly in the symphony of control. Control theory, at its core, is about mastering the art and science of precision. It's the discipline that empowers us to harness the power of machines, systems, and processes to achieve desired outcomes with exactitude and efficiency. Here's a comprehensive look at how control engineers and practitioners master control. The journey to mastering control begins with mathematical modeling. Control engineers create mathematical representations of a system, often using differential equations and transfer functions. These models capture the dynamics, behavior, and relationships within the system. The ability to translate real-world phenomena into mathematical equations is fundamental. Control engineers employ mathematical tools to analyze system behavior. This includes stability analysis, frequency response analysis, and transient response analysis. Understanding how a system responds to different inputs and disturbances is essential for designing effective control strategies. Control design involves crafting strategies to manipulate a system's behavior to achieve specific goals. Engineers select control algorithms and parameters, such as PID controllers, state-space controllers, or advanced model predictive controllers. The art lies in finding the right balance between stability, performance, and robustness. Feedback is the linchpin of control systems. Engineers design feedback loops that continuously monitor system performance, compare it to the desired values, and apply corrective actions. This loop ensures that the system remains on track despite disturbances or uncertainties. Once control strategies are designed, they must be implemented in real systems. This often involves programming controllers, configuring sensors and actuators, and fine-tuning control parameters. The ability to adapt control strategies to practical constraints is a key skill. Precision control relies on accurate sensing and precise actuation. Control engineers work with a variety of sensors, like encoders, accelerometers, and cameras, to measure system variables. Actuators, like motors or valves or servos, execute control actions. Choosing the right sensors and actuators and calibrating them correctly is critical. Control systems must be robust to uncertainties and variations in system dynamics. Engineers employ techniques such as robust control and adaptive control to ensure that control strategies work effectively under changing conditions. Optimization techniques are employed to fine-tune control strategies for maximum performance. This includes optimizing control parameters, trajectories, and energy usage. Optimization also plays a role in model-based control and predictive control strategies. Many control applications require real-time decision-making. Control engineers design algorithms that can execute control actions within strict time constraints. This is crucial in applications like robotics, autonomous vehicles, and industrial automation. Control systems often interact with human operators or users. Human factors in user interface design are essential considerations to ensure that control systems are intuitive, safe, and user-friendly. Control is an evolving field. Engineers and practitioners engage in continuous learning to stay updated with the latest advancements in control theory, sensor technology, and computing power. This adaptability ensures that control systems remain at the cutting edge of precision. As control systems become more autonomous and pervasive, ethical considerations become paramount. Control engineers must consider the ethical implications of their designs, including issues related to safety, privacy, and bias. Mastering control is a multidimensional endeavor that combines mathematical rigor, engineering creativity, and a deep understanding of system dynamics. Control engineers and practitioners are the architects of precision, applying their knowledge and skills to shape the behavior of machines and systems across industries. In a world where precision is synonymous with efficiency, safety, and quality, the mastery of control remains an ever-relevant and evolving pursuit. The interactions between components in control systems are the secret behind their ability to achieve precise and adaptive control. They form the intricate web that connects theory to practice, transforming abstract concepts into real-world achievements. As we continue our journey through control theory, remember that these interactions are the melodies that compose the symphony of control, producing beautiful outcomes in diverse industries. In the journey through the world of control theory, we've embarked on a fascinating exploration of how precision is achieved in a multitude of industries and applications. Control theory, often hidden from plain sight, serves as the silent conductor that orchestrates the symphony of machines, systems, and processes. As we conclude this lesson, let's reflect on the essence of precision in control. Control theory is the art and science of shaping the behavior of systems to meet specific goals, whether it's regulating temperature in a chemical reactor, stabilizing an aircraft in flight, or guiding a robot through intricate tasks. It's about understanding the dynamics, modeling the intricacies, and designing strategies that allow us to maintain precision in an ever-changing world. At its core, control theory is a discipline that thrives on precision. It begins with the precise mathematical modeling of systems, capturing their intricacy in equations and diagrams. This precision extends to system analysis, where engineers meticulously study stability, transient responses, and frequency behaviors to ensure that control strategies are both effective and robust. Feedback, the heartbeat of control systems, operates with utmost precision. It continuously monitors the gap between desired and actual outcomes, applying corrections with precision to ensure that the system remains on track, no matter the disturbances or uncertainties it encounters. Control engineers are the maestros of precision, wielding a repertoire of control algorithms, from the classic PID controllers to state-of-the-art model predictive controllers. These algorithms are finely tuned to balance performance, stability, and robustness, achieving precise control in diverse applications. As we've seen, control systems are the invisible hands behind the myriad of industries, from industrial automation to automotive control to aerospace and robotics. They optimize processes, enhance safety, reduce energy consumption, and improve the quality of life for people around the world. But precision in control goes beyond mathematics and algorithms. It encompasses the art of adapting to change, embracing innovation, and addressing ethical considerations. Control engineers are not just architects of precision. They are the stewards of progress, ensuring that control systems evolve responsibly and ethically. In a world where precision is synonymous with efficiency, safety, and quality, mastering control remains an ever-relevant pursuit. Control theory empowers us to shape the future, harnessing the power of machines and systems to achieve our aspirations with precision. So, as we conclude this lesson, let's recognize the profound impact of control theory. and the relentless pursuit of precision in the world of engineering and beyond. It is a discipline that transforms possibilities into realities, where precision is not just a goal, but a way of life. Thanks for tuning in. I hope you found this video informative and thought-provoking. This is the point where others tell you, if you enjoyed it, please give it a thumbs up and consider subscribing for more content just like this. But we all know that kind of thing is for losers. Don't be a loser. And as always, I welcome your feedback and ideas for future videos in the comments section below. Until next time, keep exploring, keep learning, and keep embracing your inner nude, dude.